So another modification on linear regression would be to use the cosine model. And so here's the form of the cosine model. So this is a nonlinear model, and it has a bunch of parameters. So it has the mean, it has the amplitude, which is denoted by alpha. It's got the seasonal period, which is here, and it's got the phase angle, which is denoted as theta. And then, of course, it's got epsilon, which are the random errors. So this is, like I said, it's not a linear model, but it can be transformed to be linear. So if we, use some trigonometry, we can move from this model to this one. I'm not going to do the trig for you. That's not my strong suit, and I don't think that it's important for you to know it. And then, instead of using t as our predictor, so in here we're trying to predict y based on t, but then we have all these complicated parameters in here. Now we're going to use two variables, x cosine, which will be the cosine of 2 pi t over 12, and x sine, which is the sine of 2 pi t over 12. So then we have this model where we've got the x cosine and x sine in it. And then we're just trying to predict alpha, which is equal to the square root of beta 1 squared plus beta 2 squared, and theta, which is tan minus 1, the inverse tangent, of negative beta 2 over beta 1. And then we can think about this linear model like this, where we've got beta 0, beta 1 times x cosine plus beta 2 times x sine. So the cosine model is going to be useful for data that has some periodicity to it, that it has some repeated pattern over time. I'd like you to get some intuition about what those different coefficients control. And there's a Shiny app. I think it must have been made by one of the authors of our textbook. And I have it linked in the slides, and I'll put the link on Canvas as well, so that you can go look and see what those coefficients do. All right. So here we've got some data. I think this is data that the book talks about the Peace Bridge and the traffic over time. So each of these circles is one point in time, and this is how much traffic there was on the bridge. And then they've been connected together. The black line is the real time series, and we're trying to come up with a good model fit using the red line. And so we can adjust things like the amplitude, to make it more or less bendy. And we can adjust the theta to hopefully scoot the curve to the position that we need it in. And then we can adjust the constant to hopefully move it up near the real data. Maybe I need to scoot it. All right, maybe we need a bigger amplitude to kind of capture more or less of this. So again, this is, R would do this for you. It would find the best fit model for the data set, but you can try and get it as good as you can. And we want to minimize the sum of the squared errors. So right now I have 83,428, and you could see if you could get a better SSE than I could, maybe by adjusting the parameters somewhat. All right, so I said that the cosine model is good for data that has some periodicity. The clothing expenditures data didn't have periodicity, so we're going to think about this example of butter imports. So in this data set, I have data which is collected on a monthly basis, and then I have the Danish butter imports. And so I've got data on how much butter was imported. Not sure what the units on that variable are. But if we look at the time series plot of the butter imports, there's clearly some periodicity here. So that looks like something that a cosine model might do a nice job of modeling. So in order to model this, I'm going to create the two variables x cosine and x sine, and then I can plug those in as my predictors in my linear regression model. And so again, I don't have a nice sentence for these coefficient estimates, but we could plot the model fit. Again, the model fit is the blue line. I think that it looks visually like it's doing an okay job. It's capturing some of the variability there, but we might be able to do better with another type of model.